Hey, Catherine here. We're going to give everyone a couple more minutes. All right, guys, well, I'll start in another minute. See if anyone jumps on. All right, well, 6:05. I'm going to hope that, everyone's going to come in here soon, but it's a small group. So if you have questions, feel free to stop us. I guess to get started, my name is Rachel, and myself and Vidullan are part of the Autonomous Robotics Competition Club here at Penn State. Is primarily at this point aerospace students. It started as an aerospace engineering club. We've now expanded. Vidullan and I are both graduate students in the aerospace engineering program. It happens to be mostly graduate students at this point, probably 80%. But obviously, due to COVID, it's been hard to engage undergraduate students at this point. And as is described by the name, we primarily do competitions, and that's why we exist, to do competitions related mostly to unmanned aerial systems. So that's what we're going to talk about today, is some of the work, technology, development, and implementation towards unmanned aerial systems is the title of this slideshow. I'll go through this for about 30 minutes, and then Vidullan's going to help you guys do some coding in Python and integrate your own webcam-based visual tracking based on color. So hopefully you guys stick around for that. And again, small group, so feel free to stop me at any point. All right, so the first project I want to talk to you guys about is our first responder long endurance UAS competition. And honestly, I always like a video, so I'm going to hope that you guys can hear this as well. But this is a flight test that we completed at the beginning of February. You can see as evidenced by lots of snow going on here. This is a 50-pound octorotor, so 8 motors, 8 propellers. It's a fuel-powered system, so you can see a fuel tank, and we'll see that later with a generator. 50 pounds total, carrying a 10-pound payload. And yeah, I'll just play. This is the takeoff. Yeah, so it's hard to tell in this photo. You'll see on the ground, but currently we changed the heading around so that we could get the onboard camera get a view of us on the ground actually. So that's not what I meant to do. All right. But now I'll talk about the overview of what's going on here. Why are we doing this? So this is funded and actually motivated by NIST, is the National Institute of Science and Technology. They were looking for a vehicle that is low cost, So under $30,000 is their definition of low cost. This is currently at $15,000. Fully autonomous to include obstacle avoidance. So that's currently, our current work is to implement a LiDAR camera to make this able to detect obstacles by itself and navigate. So that means doing path planning to reroute basically if there's an obstacle in its way. So that's the current work that we're doing. And the video you saw was the first autonomous takeoff, and went through and actually did a 30-minute flight. So that's the other big motivator for this project, is high endurance. So we talked about fuel before. That's why there's this fuel tank and generator on board. Generator you can't see is in the back of the vehicle. But we're estimating that this vehicle is going to be able to fly for over 3.5 hours. We're shooting for 4. And so again, a vehicle at that cost, at that endurance, able to carry a communications payload. So ultimately, this vehicle would be used for first responders who were responding to a missing person. Somebody lost in the desert was specifically the case that motivated this project. And so we're going to go through, and I'll talk quickly to what motivated some of our design decisions. But you can see kind of a summary to our approach here. High efficiency motors, the generator's got the power needed to carry the vehicle described. There's batteries that you'll see for backup power in case the generator has a problem. And kind of the rest, yeah, you'll see. Well, that was our video. This is typical data that we pulled from that flight. So again, I'm just that we're looking for during a flight test. This chart specifically, the red and green are the motor outputs. So that's, you can see basically the power required to hover, because this vehicle again hovered for about 30 minutes. And you can see this initial takeoff, ramp up to takeoff, and then also land. And then the blue is the altitude. So again, we were hovering about 15 meters above ground, and it was about 20 meters as measured by the barometer, and that's above sea level. Yeah, just an overview of this entire system. You can see in the middle here describing the vehicle as operating autonomously, again, being able to navigate between waypoints on its own, even in the midst of obstacles, whether that be moving obstacles such as another drone or a bird, a commercial airplane, whether this isn't hovering at that height yet to be worried about that, but or it could be trees, unlikely in the desert, but if this was going to be expanded to further search and rescue missions that would be encountering static and dynamic obstacles. And so you can see this is a chart that was required by the competition. So one of the unique things about this work that we did, this required several presentations to the sponsor throughout the competition, where we had to demonstrate that we were making progress towards that. Again, it was much more of a typical developed project funded at each step. So we've earned over $20,000 to complete this project. When the vehicle costs $15,000, that's not all that impressive, but obviously we're succeeding and making it through the phases. And so these are just charts that we were having to explain our decision making. Again, I'm exposing you guys to this. If you're not hardware oriented, these are some of the things that we need to facilitate then also our autonomous development. So propulsion subsystem, this is the motors, the propellers, and you can see here a couple points of, we bought these from company T-Motor that's developing these. So again, having to calculate what's an acceptable throttle, how many watts of power do we need for each motor at hover, and then also accounting for if there's wind. So you can see here that it's hovering at about 64% throttle, and the reason why we were shooting for 50 to 60% is that you want to have extra power to do high-powered maneuvers, such as accounting for wind or other disturbances. And then you need more power to climb to hover for in between. So that's why you shoot for something lower, you know, trying to not exceed 80–90% throttle at any given point. Yeah, as you saw before, is the fuel tank and generator system is actually developed for a hybrid drone with enough power for 4 to 5 minutes of backup batteries, LiPo batteries, in case the generator has some kind of failure, or if you ran out of fuel for some reason. Here where it's get a little more interesting. If you worked with flight controllers at all, PixHawk is a major system running PX4 or Ardu Pilot, are both open source available flight control softwares. So that interfaces to all of our onboard subsystems, including the onboard computer, where it's making calculations for how do I get to my next waypoint, path planning, and then again, going to integrate the LiDAR and other camera to measure, and then how do I avoid obstacles. So that's why you have the PixHawk. It's communicating directly with the motors and taking data from your GPS, which is also pictured here, and other sensors as needed. We're with the gimbal. This is specific 3-axis gimbal required by the competition for navigation, and also for, you know, we're using this camera to actually, Vidullan's work is related to, can we do some object detection or image classification? Is there a person in this image? So I showed you where the vehicle changed its heading during that flight. And that was to get pictures on the ground so that we could train our system to recognize people that height on the ground, so that can maybe help a first responder who might not be able to watch the camera on the ground the whole time, trying to find somebody again in this scenario. So just another way that this vehicle would be able to help first responders. And then just calling out our onboard computers, a simple Raspberry Pi does everything from onboard fuel monitoring. So we have a good idea of how much fuel we're burning, a good estimation, but this gives you real time how much fuel do you have left. And then now we're expanding to higher levels of autonomy again, basically navigating obstacles. This is just the radio that we use. Again, if you're familiar with aircraft or see aircraft at all, you'd be familiar with Spectrum. This is how you communicate on board for manual flight specifically. Then similar, this is the telemetry. We have joystick for control of the drone and camera as well, integrated with some of our other ground control software that we'll use later. But similar idea, communicating with the vehicle on the ground in case of an emergency if the autopilot wasn't working for some reason. This is our video link. So again, being able to get image on the ground, video on the ground, real time. This is a very brief overview of our own in-lab ground control software. So I talked about PixHawk as a very common off-the-shelf available system that includes a ground control station, but we actually have our own developed in lab. Again, this is Eric Johnson is my advisor specifically in the aerospace department. So this is utilized from anything to an autopilot to ground control and some higher levels of autonomy that are described here, anything from obstacle avoidance to formation flight, so flying with multiple vehicles at one time. And so at this point, I'm actually going to switch over and show that system real quick. I'm gonna remember to share the right screen. Yep, all right. So if I can get it. So this is also available. As you can see, we're very active on YouTube. Now, we have a couple videos here for the lab is Pearl, Pennsylvania UAV Research Lab. So a couple of the, or just one of an example of just a simple quadcopter. This is actually not GUSS, this is just a vision based, so it's detecting the lab space. Again, this would be useful for vision-based navigation, either indoors or outdoors eventually. So again, it's flying around the lab and tracking where it thinks obstacles are. And you can see it's even creating a map, kind of memorizing, again, where things have been detected. But very early stage here. But obviously this is a very small drone that this is integrated on. Would be fairly useful for any sort of indoor drone flying. The other one I wanted to show you that was actually the onboard. So this is our onboard ground control, onboard flight control and ground control. So this is what you're seeing on the ground. So there's a quadcopter model in the ground station. So it's showing what's happening. You can see up here, maybe you can see up here in the right corner of this vehicle actually flying in someone's basement. But here it's telling you on the ground, you know, you've taken off. It's hard to tell, but it's doing autonomous flight now is also indicated on the screen. This is the waypoint that it was given. And then a commanded change of position is what it's doing now. So again, very brief exposure to some of the things that go on related to our research and also the competition work. You can see the vehicles changing heading is what's represented by these orange lines here, and now it's going to land, which was detected. Okay. So I just want to show that real quick. Again, a lot of the stuff we do for competition work is commercial available, you know, things that are easy to implement, that don't require a lot of adaptation for, you know, based on that. So that's why PixHawk's really nice, but we do use GUST and other in lab developed stuff. So one of the competitions that have actually completed was back when we could travel internationally. This is the International Micro Air Vehicle Competition back in 2019. I'm gonna do it this way. Do a new share. All right. So this is available on our page. I'll bring it up so you can see. The right thing. Okay. So this is a very brief overview of our expertise, but really what I wanted to show was displays our past mission. So this is IMAV 2019. One of the missions or overall goals was doing mapping using the drones. So this is actually the competition field. There'll be a little more detail later, but these are a collection of images that were gathered on 3 different drones that were all stitched together off board. So yeah, you can see kind of the final product there. There it is again. This is actually out at Ag Progress, similar technique when we were testing back here. You know, Ag Progress is near Penn State. That is where we do some of our test flight work. So another main part, along with the mapping, was detecting objects, including what was simulated as a red mailbox, different color, red, blue, and yellow mailboxes. So you can see here, there's a blue helipad. So again, this is back at Ag Progress when we were testing out some of this, but you can see here where we've tagged it with the GPS is tagging, you know, the location of these objects as well. See why that's important. Again, blue mailbox at the top of the screen is a little hard to see. This is like the actual competition. The orange boxes were also important, red mailbox. So the third part was then delivering a package to those mailboxes. So you can see this vehicle is one of the 3 that we had going at one time, which I'll discuss a little bit more. But again, you can see it taking off with one of those packages that it's going to go deliver to those mailboxes that we detected, which is what this is doing now. Again, this is all autonomous. The vehicles, give commands to start a mission and do different steps along the way. But this was all all determined based on that mapping the object did, or the vehicle did. So you can see that was an example of a successful package delivery, which was exciting, and others were a little close. Again, that was the ultimate goal, the outdoor mission. There was also an indoor mission, was warehouse inventory. That was another big part of drone use, is indoors. So you can see our team member there doing indoor work, and a group of us, again, here in Madrid, Spain. It's kind of the benefit of doing this project. And we'll describe a little bit more, but you can see the vehicles there and some of us doing this real time. We jump back to outdoor. Again, I think we took 7 of us to this competition total. It's been a week in Madrid. Now you can see our 3 vehicles for the outdoor, where they're weighing it, because weight was a big factor. And I'm going to stop there. Go back. Yeah, so I can talk a little bit more about those competitions. Again, feel free to stop me at any point. This is a brief overview of that indoor competition, the warehouse mission. And yeah, kind of 4 different missions in that, including mostly to log packages and cross in between shelves, and then pick up an object and deliver a flag that you determined, or used visual methods that are kind of described here. Again, very basic. If you're used to doing any data training like RCNN, this is an example of some of the training images that we produced. So the flags were part of what the vehicle was supposed to be able to recognize. So it's recognizing, okay, here's a flag, and now I'm going to store this image to recognize it, be able to match it to a different flag later on in the mission. These are just training images. So trying to take different examples of flags at different angles, not knowing what this was going to look like at the competition. They did help us out with the white background, but you can see this, again, just a very basic, trying to train this method to be able to recognize flags in different scenarios. And then this was so it's QR based, where it was tracking both a general shelf QR code and then matching package QR codes to each shelf. And again, this would be helpful where you wouldn't have to have a person doing inventory in a warehouse, but have just this drone go out, the QR codes based on inventory it had in its database. I think you are familiar with. An example of what was testing. Yeah, another big part of this was navigating between the shelves. So again, it's only useful if the vehicle can do this all on its own without having an operator manage this motion, in between shelves. So one of the methods that we used for determining if a shelf area was safe to cross, meaning there weren't packages in the way, an absence of QR codes above the shelf can indicate a safe crossing area, so meaning an empty shelf that it might be able to fit in between. And you see here some of the measurement images. Again, just to expose you to Penn filter measurements, measurement updates. So this is filtering the data that the camera is seeing to produce information that's actually useful for the navigation code and path planning to determine where it is safe to travel between. And of course, again, this was the area that we saw the final map from individual pictures from the 3 drones. We had 3 quadcopters all flying at the same time. Again, with this is the largest package, but our method being that these vehicles and time constraints limited by weight of the vehicle, so producing time to do the mapping quicker also made it possible to be able to actually, in this case, this drone was able to carry the largest package and we actually crashed. So luckily we had 2 identical drones that were able to pick the stacks and deliver the rest of the mailboxes, or the boxes in the mailbox. So again, part of that was creating 3 drones that were all the same to be able to, again, in a competition scenario, every time. So, but in general, yeah, we're saving images on a USB and change after landing to together and produce that final image that you saw. At the same time, tagging where mailboxes were, sensing that the drones were delivering to mailboxes completely autonomously, and then being able to deliver. Okay. Again, definitely we were able to load the packages on the drone, so that did help a lot. Where the servo that we designed was only responsible for dropping the package and not having to pick it up too. So yeah, pros are easier and more difficult parts of each competition. But here's a brief overview of the communication that's going on. So the ground control station laptop is off-board. Everything else is declared on board the vehicle. The Pi computer Pix Racer, their Pix boxes I talked about in the first work. Flight control, and the telemetry radio that's communicating to the ground station. So again, the Pi is communicating to the Pix Racer, waypoints, also mode updates. So we reach a point where we need to now deliver the package, like, now we're in mapping mode, or now we're to deliver package, and now we're able to come back home. Those kinds of things. The Pix Racer, and the Pix Racer is communicating to the motors. How do we do that? How do we navigate that? Well, apologize. Let me try and get this back up. All right, can you see this again? I'm gonna hope you guys can see. Okay. All right, thanks. All right. Sorry about that. If anyone has questions, feel free to share. This is again, as described, each drone is flying a path. Again, as before, some parts of this are easier. Luckily, we had the competition space beforehand, so we could actually define these waypoints and this path beforehand for these vehicles. And then the main part being mapping, so the drones taking adequate pictures that were able to be stitched together and produce that final result stitched image. And this took about 20 minutes off board. So once we had all the flash drive, you know, from the vehicle on the ground. And so to do that real time still requires a lot of computing power. Obviously we had laptops on the field, but just it emphasized some of the common issues with actually doing these for real-time package delivery, and why companies are struggling to do this right now. But you can see this is the localization kind of technique, is being able to extract color. So again, we knew red, blue, yellow, but what does this actually look like at the time of day that we're operating at? Because these colors look different depending on what time of day you're at, where the sun's at, if it's cloudy. So we were actually having to adjust the range of color that was being looked for. But when it works, this is what it looks like. That, you know, it's looking for yellow, it's found yellow. Now we want to know if it's a square, because again, we knew the package delivery zone should be a square. It's decided that this blob over here is not a square, so we're not going to identify that as a delivery zone. And then finally, if it is a successful, you know, target, it's going to tag the GPS location. So again, it doesn't always work. Here's just a small blue square that got tagged as a blue mailbox. And then this you can't really quite see, but this was a yellow mailbox successfully identified. And other similar pieces, the red, your real blue, and what it looked like, you know, color and then shape. And some orange packages we were supposed to identify as well. And then again, you saw this, but a similar landing. Again, just at this point, the vehicle is operating completely autonomously. Once we put the package on, we tell it to go deliver. It knows this location from the previous mapping it's done. We actually lucked out a lot because there was some wind on that day. And obviously, we were dropping them at a pretty high altitude. We could have chosen to go lower, but that's for time reasons. That's what we did. Yeah, so at this point, does anyone have any questions? Just talk your ears off for a while. Work we do. I don't know what your backgrounds are in, but it's a lot if you're not used to air vehicles. Or unfortunately, our one ground vehicle competition was supposed to happen last year, and obviously hasn't yet. So we are supposed to do other. We're the Autonomous Robotics Competition Club, but we do tend to do a lot of aerial robotics work. But yeah, otherwise I'm going to hand it off to Vidullan, who's going to actually do the fun part with you guys.
Yeah. Thanks, Rachel. That was great.
Yep.
Yeah, people know about our club now.
Yeah, you can always look us up.
I've shared pictures of the big aircraft and stuff you're building right now.
I should share that. I'll pull it up.
Yeah.
Yeah, we're about ready to flight test a big fixed wing, but
I just posted a message for everyone who wants to see the code or code along. You can just click on the link. There's all the code there. So. Are you pulling up the images? Rachel, are you getting the images?
yeah, sorry.
Oh, sorry, I wasn't sure if you were.
see how well my internet's doing right now. You better start. It might take me a minute or two.
Yeah, I'm struggling with sending the code out.
Okay. Yeah, I guess I can talk briefly about, okay, I found it. My computer's doing a good job. All right. I'm gonna share my screen again real briefly. I won't talk too much to this, but this is physically from today, earlier today. This is a big fixed wing aircraft, airplane that is 14-foot wingspan. And I literally just finished putting it together today. Oh, no, that's just mission planner. But we're using this for the International Aerial Robotics Competition. It is supposed to happen in August. We'll see. But requires flying 2 miles out to a simulated boat. So there's a mast on a motion platform. Actually, we'll just let's go. Let's get that. A lot easier. Yeah, so this is, if you're ever interested to look at some really involved competitions, this one is one of them. And this requires a combination of long endurance flight, which is why we have the airplane, long endurance and fast, so much faster than a quadcopter. But then we also have, we're going to drop a quadcopter from the fixed wing in the middle of the air. So we're flying, we're going to drop the quadcopter to then deliver this block, if you can tell, onto this mast that's also moving on a motion platform. So anyways, that's a lot, but that's what we're working on right now. This is an international competition. Again, there's a venue in the United States and a venue in China every year. And yeah, it'll be interesting to see if, whenever it does happen, if it's this year or next year, which teams are able to complete this task, because this also requires to be done in 9 minutes to fly a total of 4 miles and do this mission, which involves, again, tracking the mast. So the vehicle predicting the mast motion, and then actually being able to fit the block on correctly, all autonomously. So, but the fun part's I got to build the airplane, so I guess I have that going for me. But yeah, that's the type of work you can do if you want to join us. You can also see our other vehicle back here. So this is a lab space out at the hangar at the University Park Airport is where we work out of. I will actually hand it over to you now.
Cool. I think everyone can see my screen, right? I'm also not sure who's coding along, but if you guys are coding along, please feel free to stop me at any time. Like Rachel said, it's a very small group. So if you guys have any like things you want to try out, or if your code's not running, just post a message, I guess, on the chat, and then I can stop and help with that. But yeah, so the idea here was that we would help you guys code something that was similar to what we do for competitions. So I guess in robotics, yeah, there's a lot of like sensor integration, there's computer vision is part of that, and then using that information to then control your robot. Unfortunately, because we're not in the lab, it's going to be hard to do the robot side. So I thought it'd be great if you guys could just see the computer vision side. So there's a folder on OneDrive. If you guys are following on and want me to stop and wait for you guys to get it, just let me know. But that folder has a bunch of code, a bunch of images, and that's all you'll need for today. I think the only other thing you'll need is Python, right? So just open up my Python. And the only thing you would have to do once you have Python is just install OpenCV Python. Right? And I already have it installed. But I guess if you're following along and you don't have it, that's the command you have to use. I'm gonna make this bigger. Yeah, so that's the line, I guess. Yeah. Just trying to make sure. Can you guys see, Rachel, can you see like what I'm typing, or is it too small?
I can see it okay.
Okay.
Somebody asked you to send the
Yeah,
link.
I'll send it again. It's odd that the chat doesn't, oh, there it is again. So there's the link again. Hopefully everyone got it. Yep. I'll give them a few minutes to download that. In the meantime, I guess I'll just go over basics. So I guess the only thing you have to know for this thing is kind of how images are stored in your computer. So every picture you take has these three arrays, I guess. So just like a column, a bunch of columns and a bunch of rows of numbers. And each of the numbers goes between 0 and 255. So 0 is like no red, and 255 is just purely red, and all the shades in between. So you have one for your red, one for your green, and one for your blue. So that's why they call them RGB images, because there's like one for red, one for green, and one for blue. And if you had like a black and white image, this would just be only one of these, and it would be 0 would be black and 1 would be white. And the way an image is formed is in each of these boxes, you have like a number, and then when you combine all of them, you kind of see the picture you're seeing, right? So let's say you want to, I don't know, you have a picture and you want to just keep only the red color. You can just set these other two matrices to 0, and that would make sure you only have the red color. Okay? And that's kind of what we're going to do today, kind of manipulate these colors and see what we can do with that. So I'll lay out the overall task. Okay, so I got this video clip from YouTube, and all it is someone juggling, right? It's a really nice video, like it's really high definition, so it should be easy to catch out these balls. And what we're trying to do is see if we can, you know, see one of these, the red ball maybe, and see if we can follow it around, and also see if we can kind of maybe predict where it might be in the future. That's something that's pretty common in robotics. You want to like get some input from your cameras and kind of predict what the person is doing or what's happening, or maybe you want to predict, maybe you're building a car and you want to predict where the other cars are going so you don't hit them. Maybe you're building a competitor Tesla or something. Okay. So from this image part, we will, hopefully all of you guys have OpenCV now. And just like if anyone wants to type in the chat, hopefully all of you guys can code in Python, whoever's coding along. I'm going to assume everyone can code in Python. So first we begin by importing the library. So if you guys open up the shapes.py file, it's in the OneDrive box. I guess the first part is just to include your library, and this is CV2 is OpenCV. It's a very common library. It's like maintained by Intel. It's has a lot of algorithms for computer vision, and it's free, and it's available for everyone, and it's pretty up to date. The only caveat would be that it has a lot of classical vision techniques. And what I mean by classical vision is a lot of today's vision is done with like deep learning and neural networks. But these are techniques that don't use any of that, like how things used to be done. And these techniques are still in use today. You kind of have to do these things first before you use your neural networks. So it's good to know these things. So I guess we'll start by first. Let's do this. And I'll run this file. I guess you guys can't see the output. Maybe one of the organizers knows how to do this. Do you know how to share the whole screen instead of just the window? Anyone?
I don't think it's an option on a webinar. You're going to have to just share each individual window at a time and jump around, unfortunately.
Okay. I'll try to do that, yeah. Okay. Right. There's going to be a lot of jumping around. But, so it should open this image up. It's just a random image I made in Paint. I'm a future great artist, so my Pac-Man looks pretty good, but has a bunch of boxes, different colors, and a weird like half circular shape. And I guess the first step to do is figure out if we can pick out different colors from a white background. It's like probably the easiest option because there's a huge contrast between the colors. So the first thing we did was that, just look at the image. Whenever you want to find the differences between the boundaries, the way to do it is actually, whenever you have color, like I showed you, there's 3 of those matrices, and you don't really need all 3, and it makes it harder. So first step we're going to do is make the image into a grayscale image. So just take that color image, get rid of all the colors, because all we need is just a black and white image to figure out where the colored parts are, or where the shapes are, right? So that's what this does. It just tells it, convert this image from red, green, blue to gray. OpenCV actually stores it backwards, so it's blue, green, red, but it doesn't really matter. And then what we're going to do is use this thing called a threshold, which is, let's stop my screen share again. Okay. Yeah. And the next, so this is a part where we convert it to grayscale. And the next thing we're going to do is threshold the image. And what I mean by that is, so going back to these, since we're trying to segment the objects, and now they're in black and white. So we only have like one of these matrices. So let's say we only have the red one. What you're trying to do is say, if the color in a spot is below a certain number, then make it a 1. And if it's above a certain number, make it a 0, or as the opposite. So that way, what you can do is, because you know the background is completely white or black or a certain color, you can pick out the background from the foreground objects, because you know there's a big difference in color. So in this case, what we've done is, I'll show you guys what the black and white image would look like. So yeah. Switching again. So that was our original image. Then we converted it into black and white. And you can see that the color information is gone, but the background is still extremely white. And the objects now, because they're not white and they're colored, they're in some sort of weird grayscale. So now what I'm going to do is say, okay, if the background is 255, which is white, then make it black. And if it's anything else, make it white, or the opposite, right? So that's what that threshold is. And as soon as I do that, you can kind of see how the background is gone and I've just got all these squares. And what this is called is like a mask, because you can superimpose this onto your image and get just the sections that are white. Because what this really means is, in that matrix, all of these numbers are 0, and you only have 1s or 255 wherever the objects you want to detect are. And that's, I guess, one of the fundamental ways of doing things. Yeah. Okay. So once we do that, now we need to kind of go ahead and figure out what the actual, like, we somehow have to find a way to draw like circles and squares around those white portions to actually extract them. And you don't have to actually do this. There's like algorithms to do this. They've been developed like long ago. And OpenCV provides the functions for you. So all you have to do is just tell it, hey, find all the contours in this image, which is that black and white image we just made. It's called a binary image because it's not just a black and white grayscale image. It's just only black or only white. And so it takes that image and tries to find all the edges in it, right? Just make a simple approximation and then give me like, just give me the output in this format. That's what this is, right? So we're gonna get a bunch of points that belong to each of the objects that'll be stored here. And this one tells us how they're all connected to each other. So for example, maybe you have an object inside another object, and this would tell you that. In our case, we don't. They're all kind of separate from each other. The only thing you have to be careful of is doing this. I don't know if you guys have coded in Python before, but usually, let's say you had a variable a is equal to 1, and then you have, b is equal to 2. If you do b is equal to a, then now whenever you like output b, the value of b would be 1, right? And then let's say you go ahead and change b is equal to 3, a is still going to be equal to 1, right? It's not that the value of a changed, even though you changed b. But when you work with images, if you go ahead and do this, then anytime you change this image also changes. It's just implemented that way in memory, so it's faster. So you just got to be a little careful when you're working with images with OpenCV. Instead, you want to use this. This actually makes a copy of the image and stores it in here. So even if I delete this or change it, the original image doesn't change. So once we do that, once we detect all the contours, they also give you a way to draw all of them so we can see what they look like. So that's what we've done here, and I'll show you guys what it might look like. And I'm going to draw it on our original image so we kind of see it. And I'm telling to draw all of them in this color. So that's blue and that's green. So I'm only doing like green. And this is how thick the line is, right? Okay. Try that again. Cool. So that was the original image. Then we went to this black and white image. Then we used the thresholding to create this binary image. And on this image, we try to find all the contours. One thing to see is that kind of in here, there's a little bit of noise. What is noise? What that means is there's like some random pixel that showed up as white, which shouldn't have. And we'll also see how to deal with these sort of things. In real world images, if you take a picture from your webcam, you'll get a lot of these all over the place, and you kind of have to deal with that. And then, so this is the output from the contours. So it kind of has figured out that, you know, all of those white things are shapes, and I'm going to draw like points around them and then connect them. And it's also connected this point. So now we know that I have this many shapes, but the thing is the computer really doesn't know what the shapes look like, how big they're. It just has a bunch of points that are connected to each other, right? Cool. So now the question is, how do I go through that thing and figure out which of the shapes is like a square or rectangle, which one's a circle, what's a triangle, and I mean, what colors are each of those things? Because if you remember when we're trying to do like the juggling example, we need to be able to figure out circles, and we need to be able to figure out what circle is what color, right? So those are the two things we're going for here. So in this case, like I said, I drew all of them at once. So when I say -1, it means just draw all of them. I'll do this. Also comment this out. So I don't change the original image by drawing stuff onto it. And here's how you can draw each one by one. So I made a copy of the image so I can draw on it and not mess up the original. And what I'm going to do is this contour, if you want to see what it looks like. So you can kind of see here, what that contains is a list of different contours. So it's actually like a list of things. And inside that list, it has a bunch of smaller lists. And each of those smaller lists is one of those shapes. So what you can do is go through each of those shapes inside the list, and you can draw them separately, right? So that's what this is doing. So you can see it. So for example, went through all of this. You can see kind of this one's highlighted now. Next, it drew the small one. Now it's drawing this. Now it's drawing this. So that's how you cycle through each of them. Okay. Also, does anyone have any questions, or is anyone stuck so far? Please let me know in the chat. So now that we have those things, we got to do something with them. And that's what we'll talk about next. Get rid of this. There's something called like properties. So what if you want to know how big each of those blobs are, or you want to know if they're rotated, you want to know if they're big or small. They're called moments, and all it is some mathematical functions that kind of tell you those type of things, like tell you what the area is or the volume or how big they are, right? And the way to find the center of each of those blobs is you kind of use this moments function, and it gives you a bunch of values. So this is always the same. So I guess you just, unless you want to understand how moments work, you can just calculate the moments and do this operation, I guess. And then you get the center, the X position, and the Y position. Next, what you can do is you can calculate how many dots each of those blobs takes. So that's the area, right? The bigger something is, the more the area would be. So they also have a function for that. You just give it the shape, and it will give you the area of the shape. And then the next thing is, for example, so for example, the area of this thing is, this is a square. So if I try to draw a box around it, it would kind of fit perfectly. But when I try to draw a box around a circle or a shape like a square, you're going to get some additional areas because it's going to draw a box this way, right? So what you can also do is kind of try to draw like a polygon, which is, I guess, a square, a shape with a lot more sides than a square, right? And the number of sides is something you can set. But what OpenCV tries to do is it tries to approximate this by drawing straight lines. So it might draw a line here and a line here. So it's never going to be perfect, but it kind of gives you an idea of how many lines does it take to go around this shape. Right? So what we can use that for is, it would only take me 4 lines to go around a rectangular shape. So I know if it only takes 4 lines, then it's probably a rectangle. If it takes a lot more lines, then it's probably some circular looking shape. Now it's hard to tell exactly what it is because this would also take a lot of lines, and so would this. But at least you know it's something that's kind of circular. If it's a triangle, then you know it's going to take exactly 3 sides, right? Okay. And so that's what this does. It draws a bounding rectangle around those shapes. Once I have that, I want to know if it's a square or a rectangle. So I calculate the aspect ratio, which is, I'm just seeing how much wider it is than its tall. A square would be 1, right? The width of a square is the same as the height. Then I can also calculate the area by doing W into H, so which is just width into height. And what this kind of tells me is, if it's actually a square, then the area of all the points, which is calculated from like the contour lines that I drew around, would be the same as the box I drew around, right? But if it's a circular shape or irregular shape, this square area would be a lot greater than this. So that's one way for me to check, right? And this is the one that tries to draw straight lines around it. And so we can kind of see what the output from each of those things looks like. Probably gonna print. Stop from printing all the other things. So if you guys kind of remember, this was our picture. What this is telling me is it's found one thing. Yeah. It's saying that one of the shapes has an aspect ratio of 4, which means it's, how did I say it? Is it width over height? That's what I did. Yeah, which means the width is 4 times as long as the height. That's probably this thing, right? It's way longer than an install. It tells me that tells me that the area that we are printing here, which we just calculated by multiplying the width into height, is this. And it's also telling me that the area that was calculated by counting all the points from our contour is this. And if you can see, those are pretty similar. And that makes sense because if I draw a box around this, it would pretty much enclose the whole thing. Okay? And that's the same thing that's confirmed when we draw the polygon. It tells me that, it took 4 straight lines to get around this whole thing. Just ignore this for now. I'll get back to why I did that. So I can kind of tell from there that this is probably a rectangle that's going sideways. Then there's another thing that is pretty close. So the width is pretty similar to the height. Its area is this, but the area of the rectangle is a lot bigger. Now, when you have a circle, the height and the width are pretty similar. So I can't really tell if this is a square or a circle right now. And you can also see that the area is a lot bigger. So when I draw a square around it, it's a lot bigger. So it's probably a circle, but I don't know if it's the yellow one or the blue one. Right, so that's what I'm now trying to figure out. We'll go to the next one. This one says 1, so it's probably one of the circles again. Actually, no, this might be the random point because if you notice the area is 2, and these are all so much bigger, which means whenever you see a very small area, you can kind of just ignore that point because that's just random noise. That's one way to figure out if something is like random noise. So we'll skip that one. And then we have this one, which the area of the square that goes around it is similar to the area on the inside. So it's probably this square. And then the last one, where the area is much bigger. So it's this one, right? So now the question is, which one of these is this one? And which is the other one, right? So we know these are the 2 circles. It's either this or it's this third one. Right? And the way we can do that is kind of looking at the area of a circle. That's what this is doing. If you assume one of these is a circle, and you kind of assume that the width, if I draw a square around this, that would be like the diameter. You kind of calculate the area of the circle to figure out how big the circle is. And that's why I did the calculation of an area of the circle, which is just pi r squared. It doesn't make sense for the squares, but at least for the circles, we know that this one is much bigger than this one, which means this is probably, so I know it takes a lot more straight lines to get around it. So it's something big and circular. And I know the area is a lot bigger. So this is the blue one. And this is smaller, so this has to be the yellow. So hopefully that kind of makes sense on how we kind of use these random different techniques to figure this out. It sounds a lot like we just try things out, and that's kind of how it is. You just look at your data and you kind of try to piece together, like you have a bunch of tools and you're trying to figure out a solution. It's like solving a puzzle pretty much. Right? And so using all that information, what I can do is I found the centers out here using the moments. So I'm just going to draw like a circle at the center. Then I'm going to show you guys what that box we drew around is. And we'll look at what that looks like. Oh, so I got a message saying that the voice was not that good. Is it better now? Oh, I think Anish messaged something on the group. Just let me know if it's still bad or if it's getting better. So if you can see, that's kind of what we calculated. So you just put the circle at the center, or the dot at the center, and then this is the square we drew around it. Right? Same thing here, and then what we would expect is a square around this way. Here's another point that is kind of random. This is probably the point that just said an area of 2. So obviously you can't see the square because it's really tiny. And here's this box. We draw a square around it. And finally this one. Okay. So now that you kind of know how to draw a box around it, right? Can we use those boxes to then kind of detect what the color is inside that box, right? So we're going to use the same technique we used before this to generate those binary images, which we used to pull out the shapes. I'm going to create an empty image that's just black. It's just all zeros. And in a certain spot of the image, I'm going to make it all like white. And the spot I'm talking about is the square I drew, right? So I know I drew a square. So when we calculated this rectangle, which is a rectangle that is drawn around sorry, one second. Okay, so this is the square we drew around each of those boxes, right? And so I'm just gonna literally, so I know at what location I started drawing the square. So that's X and Y. So what that means is like, that's X and that's Y. So let's say I started drawing that box, 2 boxes to the right and 2 boxes down. So that's my XY location. And the width and the height is telling me from here how many boxes wide it is and how many boxes tall it is. So just those 4 numbers tells me where to draw that square. So I'm going to use that information to go to those parts of that black image and make those squares, like those blocks, a 1, and everything else a 0, right? So that's what this is. So if you guys want to see what that might look like, so that's what it would look like down here, because I made a black image and only put white pixels wherever that box was, and 1 here, and there's 1 here. That's the noisy one that we can ignore. Then there's 1 here, and there's a circle, but like I said, we're drawing boxes around it, so it's a box here. Okay. Just comment these out. Okay. And so now what I want to do is I want to take this mask image, the binary image, which is just whites, and I want to put it over my original image and only get color wherever the white portions are, and all the black portions, I just want to ignore them. So it's a region of interest. And there's a function called bitwise and all it does is say, if the image, the second image, the black and white image, if that image has a 1, then keep that color. Otherwise, just ignore it, right? So I'm giving it the original image and this mask, which is what we just saw right now, the black images with the white dots, white pixels. Okay. And so this is my output. This is what I'm going to get. So we'll see what that is. Okay. Okay, so this is the original image, and I'm going to get just this. Same thing here, and I'm going to get that, and this, and then this. Right. And now I have that. I can go ahead and crop those sections from the original image out. Same technique. I just say, hey, I just want from this pixel to this pixel and one direction and then this. And the reason it has the last one, this just means get me the red, green, and blue because it's a color image. If you only wanted, like, if it's a black and white image, this would just be 0, 1, or something. Right? Yeah. And now what I can do with this little cropped portion is I can count what how much red there is in each of those boxes and how much green and blue. And that kind of gives me an idea of what the mean color of that portion is. In this case, it's all like one color, so you can do this, but in a real life image, even though something looks blue, it's not completely blue. So you kind of have to use some other advanced techniques, but the idea is exactly the same. You just use a different way to count it. And so that's all I'm doing. I'm just taking one of the images. And like I told you, they're just red is the first matrix, blue is the first one, green is the second one, red is the third one. So I'm just taking the first one, which is blue, and I'm just finding the average value. Same thing for the green, same thing for the red. And then I'm going to print out something that kind of detects the average color, right? Should do this instead. All right, so we'll see the whole thing in action now. Okay, so that's where we began. Then we kind of cropped out this green bar, right? And then this is the color it's actually detecting in there. So what you can use this to do is, now that you know what the numbers are, you can kind of compare. So maybe you can have like a list of things going, oh, if the color is equal to this, then I know it's my computer. If the color is equal to this, it's my cat or dog or whatever. And you can kind of use that to pick out objects from an image, right? Same thing for this part, and it's detected that the average color is this color. That's the red one, and that's the blue one, right? Cool. So I think that's the end of that file. And what this file should have given you is pretty much all the tools you need to take that real video and detect the balls. So I'll just pause for a second, see if anything is confusing or if you guys want me to go over any one section again. It's probably a lot of information at once. You have to probably practice it, but if you go through this a couple of times, it'll make sense. And if you try it on different images, that also helps a lot. So the next thing I kind of want to touch upon before we move on is this really odd thing that you might not know about unless you maybe have LED lights in your house or something of that sort. We're always used to hearing about colors in like red, green, blue. So let's say you have a website, you're building a website, you have a LED lights in your house, or you're painting. Maybe you have something different for, I guess, people who do art. But this is what happens, right? If your red is 255, let me make this bigger. It's easy to see. If your red is 255 and your green is 0 and your blue 0, you get something red, right? So if your green is full, then you get green, and so same for the blue. The problem with this is this works well when it's a computer because the lighting isn't changing. But like if you go outside and take a picture of, let's say, a blue color bag, it's never going to be 100% blue. Like nothing in the real world ever looks like this weird color, right? It'll always be some shade. So there'll be a little bit of green in there. There'll be a little bit of red in there. And this amount of green and red in there will change depending on how much light there is. Or like depending on if you're, how much reflections there and all these little things. And the problem with that is we just looked at some code where we were detecting objects purely based on these red, green, blue values, and that will break. Because let's say you kind of figure out by testing that, okay, my values are this, and if I see these numbers, then it's a ball. And then someone just moves the camera slightly, or the lighting changes, or it gets cloudy, and then these values change a little bit, and all of a sudden you're not detecting that object anymore, right? So the way people get around this is they've managed to create a different way of representing color. It's called HSV, for Hue, Saturation, and Value. And what they try to do is, in here, the red, green, and blue are like the primary colors. Here, what they've tried to do is put all the color information in hue. And saturation is just how white or dark something is. So if you see, if I change the saturation, when I go this side, it's just white always. And this side is just that really dark hue, right, of the color. Doesn't matter which one I go to. So what you've done with this is, even if all these numbers change when lighting changes, as long as you get the hue value right, you're always going to be kind of in the ballpark of the same color. And if something gets brighter, so let's say the sun shines, or it's or there's clouds, this value would change. So what this means is you've kind of managed to compress this and set it in a way where the only value you need to care about is this. And you're hoping that when the lighting changes or people move around, that the only values that change are the saturation and the brightness, because the hue always stays the same. And that's kind of why in computer vision, you'll see a lot of people using HSV color spaces and not RGB. The problem with this is you can't actually see it on your screen, because for your computer to display to you, it has to convert this back to RGB, because that's how your screens operate. So I'll show you what this might look like on a computer, but it'll just look weird. And so this is kind of something to know. When in doubt, always use HSV. You can probably get away with RGB if you have like a perfect image where the lighting is perfect and everything. But in most cases, this is a better idea. And we kind of see that. I'll show you what that might show what that looks like. So if you go to the code files, there's one called an Rgb Color Picker. And you can just, use one of the videos. I'll use this video called Target. The videos and the video folder. And I'll run this code so you can see what it does. So this is kind of what we end up with. Unfortunately, I can't share my whole screen. So there's actually another window that will open up if you run this code that just literally has this image again. And the reason it shows you twice is because when you change this image kind of changes, but that one actually shows you what the original image looks like. But it doesn't really matter for this. So what you would do, why you would create something like this is, let's say you want to detect this target. This is something we had to do for one of our competitions. You have a robot or a quadcopter or a car, and it has to find one of these targets and then land on it, right? So you need a way of kind of detecting this target. And you look at this and go, okay, this target's red. I know a little bit about my competition, so I know nothing else is going to be circular and nothing else is going to be like concentric red circles. After doing our shapes example, we have all the tools we need to detect this, right? We know how to detect circles. We know how to differentiate them from other shapes. And we know, if you kind of know what the size of the circle is, so that makes it easier, you can kind of estimate the area. And you know to look for two circles inside each other. The only thing is we need to know what the color is, right? What value of RGB do I need to use to detect this? So you can kind of make something like this where you can kind of change these values of RGB and it will update, right? This is just saying keep all the values of red between 0 and 255, all the values of green between 0 and 255, and same for blue. So this is all the values. What this is saying is if the value of red is less than 103 in that matrix, just set it to a 0. So if I remove all the red from this image, you see kind of this disappears. And this is what I was talking about. If I remove red, even though you can't see any red in the rest of the image, pretty much the whole image goes away, right? Because in real life images, there's a combination of all these colors everywhere. But that wasn't the case in our fake like Microsoft Paint image. So what I'll do here is just adjust these a little bit, try to get the best I can. So it's not good. Yeah, so you kind of do something like this and you go, okay, you know what? This is not bad. This is the majority of my image. These are just like tiny lines with a lot, like very tiny areas. So if I find some contours with really small areas, I can just ignore them and just look for the contour with the big area because that's probably my circle, right? Now I'm going to move forward in that video. Actually, it might be a better option. This is kind of what the video looked like. Just carrying this around in a cluttered environment, which is probably what you would see, a bunch of things, people, there's a bunch of stuff around there, right? And so I'm going to play the video forward and you'll see like as we move, we're doing pretty good with this, right? We're not losing this at all. Right? But what if my goal was instead to detect this yellow line? This yellow line is like a boundary. And that could be the boundary that our, let's say, a quad shouldn't fly out of, right? I don't know if you noticed, the yellow line is still here, but we kind of lost the line. And that's because there's a lot of other things that have changed the, I guess, the brightness of the image. And all of a sudden it doesn't remember the yellow line anymore because the colors have changed slightly, right? So that was just showing you like which color to pick, RGB versus HSB. Just gonna close this. So I know we only have 30 minutes left, so I'm going to not go over the HSV one where you can, there's a code file in there which has the same thing, but for HSV. And you can kind of adjust the values there and see that it's, even that's going to sometimes lose it, but it's going to do a lot better than the RGB one, right? Okay. So knowing that much, we finally come back to our original problem, which is tracking the balls in the juggling example, right? And so here's that example. There's a file called track juggle. And what we're going to do is use everything we've learned so far to see if we can actually track one of those balls, right? Okay. So the first thing is it's not an image anymore. It's a video file. There's a function for that. It's called video capture. You give it like the location of the video. And that's how you do an image. And that's how you do a video, right? And so what all a video is a bunch of images that come one after the other. And there's not much of a difference. So there's a bunch of frames. And so that's what we're doing here. We're saying till you get to the end, which is true. I'm just going to print the frame number. And from that video, which is this variable, I'm going to read one frame at a time. This will give me the frame or the image. And this tells me if something actually came back. So when the video ends, this will be false because you've reached the end, and then we can stop. Okay. me do image. Yep. Okay. You guys can kind of see this. The way it shows it is you have to kind of press a button for it to go to the next frame. So I can show you what every frame looks like, or if you hold the button and kind of plays the video. Right? And you kind of see how a video is just a bunch of images. Now, one thing is this image is kind of huge. The bigger the image is, the more processing power it's going to take, especially if you're like on a robot, which doesn't have a big computer on it, like aircrafts and stuff, you just don't have the weight. So we'll start by making it. So I'm going to try to put this. Okay. So back here, now we see like how to view an image. So the one thing is that this thing doesn't have to be a file. If you have a webcam connected to your computer, you can just look it up. You can actually stream directly from your webcam. So you can use this to kind of stream from your webcam and then move it around your room if you want to try the same thing out. Okay. So the first thing I'm going to do is make the image a little smaller. Just resizing the image, making it smaller. The second thing is, if you notice, the image is kind of big in the sense. So that's kind of what the image looks like. And I don't actually need most of this information. This person doesn't move that much. They're always kind of standing in the same spot. Knowing that, it's kind of a waste to go through this whole image. So I'm going to try to cut out just this section of the image. We're going to use what we learned before and say, you know what, I want between this location. So this is the height, the number of rows. So I want from the top to the bottom. I want the whole height. And I only want to start. So the video is 1280 pixels wide. And so I want to go from 450 to 950, right? If you look at that. So I've managed to crop that image down exactly to what I need for the processing. Right? That's the first step. And then once you're done with that, I'm going to convert that image to this HSV color space. And what I meant before by it looks weird is that same image that we're just looking at right now kind of looks like this in HSV. So it doesn't really make sense to us anymore. This is just some random colors, but the computer understands this much better. Right? And the way you convert it between those two color spaces is pretty easy. You just have to use this function that tells it, take my image and convert it from RGB, or in our case, blue, green, red, and put it into HSV. Right? The same way we did the threshold thing before, I figured out what the values are. So I know if the hue is between this number and this number, and the saturation is between these numbers, and the values between these numbers, then I kind of get the red ball. So that's what this is. So what I'm doing is going through the image and saying, if the H value is between this, keep it, otherwise get rid of it. If the S value is between these values, keep it, otherwise get rid of it, and so on. Right? What that allows me to do already is get something that looks like this. So this is what I end up getting now, right? Like I said, this is some random noise. We can get rid of this, and this is the red ball. So the way I figured it out was that same program. I kind of moved the sliders around and figured out what works. And as I move forward in the video, you can kind of see I keep getting, you know, random positions where there's noise, but then the ball itself is mostly there, right? So Now we know how to do this, and we also now know how to take this ball and detect it, because we've done that previously, right? Okay. Okay. So I created this function called detect the ball, and all this function has is exactly what we did in the shapes. I take it, I find the contours, and then for each of the contours, I find the area, and I know how big the ball is, and the camera is not moving in or out, so the ball should kind of be the same size throughout the video. And so I'm going to use that to say if the area is between these values, and this is just something I just figured out by like looking at it a few times, then I think it's the ball. And if it is, then try to draw a square around it and tell me the XY locations of that square and how big the square is. Because once I know this, I can just put whatever I want because I can track the ball, right? And if I don't find anything, just return zeros because then I know I didn't find anything. The only additional thing is how do we get rid of all that noise that we were seeing in there? Those little white specks that show up everywhere. So there's something called erosion and dilation. All you need to know about those things is this. Okay. So it's actually something called a morphological transformation. And all it is if you have a white image on a black background, erosion is what you think it is getting rid of something. It just goes over and reduces the size. So this same image becomes this. The exact opposite, dilation, is making something bigger. So this becomes this, right? And there's something called opening, which is just doing this followed by this. And there's a lot of other combinations. You can look at it. So if you can see what opening does is when you have these little specks, if you have a little speck and you do erosion, then they're going to get smaller. And because they're already small, they're going to go away. But the side effect for that is your J is also going to get smaller. So you want to make your J big again. So then you do this dilation. But because the spots don't exist anymore, they don't come back, right? So that's what opening is. It's doing erosion followed by dilation. And that's what we're going to do. There's other versions of this, and you can kind of go through here and see all these different effects that you can kind of do. Right? So going back, that's what we did. I went in. So there's something called a kernel, and all the kernel is the way this erosion works is you pick a point and you draw like a box around it, and you say, in this box, if 5 of the boxes is white, then let this exist. Or if less than 5, then make sure this one is black. Then you go to the next box, you do the same thing. And so the amount of neighbors we're looking at is what this is. In my case, just a second. Just gonna put my phone on charge. All right. Was that okay? So in our case, what we did is we just made it a 5x5 box. This is also something you kind of get through trial and error. We did the erosion thing, trying to get rid of the little dots. And this is just telling you how many times you want to do it over and over. I did it 1 time, and then I did a dilation, and I did it 2 times. So I shouldn't lose the ball, right? So kind of to see what happens. This is kind of what happens. So you kind of start with this. We do a dilation. If you can kind of see, we got rid of all of these, but we also got rid of a little bit of the ball down here. So we do the sorry, we did erosion, got rid of all the little specks. Now we only have the ball. Then we do dilation to make it bigger again, right? It's kind of like a little trick that you can use in a lot of places. And once we've done that, now it's the same thing we did before, right? We have an image, that's a mask. We know exactly what to do with it. We find the contours, then we find the areas, and then we find the boxes. So that's all this function does, right? And so using the image, we're able to detect the ball because we know what the colors of the ball might be, or like what range they're in, right? Now, you could accidentally find something that's like really small. And in my case, I'm saying if the square I draw around the ball is smaller than 20 pixels, then it's probably not the ball. So just ignore it, right? But if it is 20 pixels, then what I want to do is I want to like do something with it, right? I want to track the ball or do something. So in this case, I'm just going to overlay an image on top of it, right? And the way to do that is easy because you know exactly where the ball is, the width and the height and the XY position. You can just take another image. You can make that image smaller to the size of the box. So that's the width and height of the box. Then you can just add the two images together, right? So I go to the position of the ball in my image and then put the new image on top of it, right? And so see what that would look like. It kind of look like this. Stop it there. Yeah, all computer scientists like cats, so I just put grumpy cat on top of the ball, right? And so anywhere it detects a ball, it just replaces the ball with this. You can add whatever you want. You can change the color of it. You can do many things. Sharing, okay, cool. And so the next question is, what if I don't know where the ball is, right? So that's what tracking is all about. It's all well and good when you can find the ball, but there's certain cases when you lose the ball. Maybe the hand is in front of it, or you know the lighting is bad, or whatever reason. At that point, you need to figure out a way of predicting when the ball is not there, right? And there's many methods of doing it. We'll just do something extremely simple. Let's assume that if a ball is going in one direction, it's going to keep going in that direction when we don't see it, right? So to do that, all I have to do is at every step, whenever I see the ball, I am just storing where the ball is. So every time I see the ball in this image, I'm going to say the location of the ball, which is where the ball is this XY position of where that square is and the center of that square, right? That's the center of the ball. You go to where you're drawing that square and go to the center of that square. So that's what this is. That's the X pixel position and then the Y pixel position. And I just store it in this list of a history, I guess. I'm just collecting all of this, right? When I don't see the ball, I'm going to say I'm going to predict it. And to predict it, all I'm doing is taking these histories of XY positions that I've had previously, kind of averaging out the change per frame. So saying it's just a standard like calculation of how far you're moving. So let's say the ball has gone 5 pixels to the left between each frame. So I can assume that the next frame is going to go 5 pixels again, right? Because I can't see it and I'm making a simple assumption. And that's all I'm doing. I'm kind of predicting where the ball is going to be by just taking the previous data, calculating the average of how much it moved, and then just adding it to, so let's say in frame number X, I see the ball at a position. Then in X plus 1, I just add whatever position was there previously, and I just add this change, right? So it's kind of a linear prediction. And whenever I can't see the ball, all I'm doing is I'm just drawing a circle instead of the cat image. So I know that it's actually a prediction, right? Using the same thing, we can go one step further. Even when you can see the ball, you can try to predict where the ball might be in the next frame. So this is useful if your robot wants to predict, or if your robot is trying to like avoid cars or avoid like obstacles. It's not just important for you to know where the obstacle is now. You also want to see where could it be in the next 1 second, so I might predict how to go around it best. So let's try to predict where the ball might be, let's say 2 frames ahead, right? Or 1 frame ahead. In this case, I just did 1 frame. Same idea, I took the current location. I have the history of like how much it's moving per frame. And I just took the current location and added this. So I'm assuming that in the next frame, it's going to keep moving the same way it always has. And I'm just making a prediction, and I'm just drawing a circle. It's, I guess, a yellow circle, right? It's 255 for green and 255 for red. So that should be yellow, right? So kind of see how this works out. Yeah, so that's what I end up with. In the beginning, there's only 1 frame, so I can't really make any predictions because I don't have history. The way I've set it up in this code, you can mess around with it, is only start predicting once you've at least seen the ball 3 times, right? So you can kind of make a couple of averages. So that's the first frame. That's the second frame. We're still seeing the ball down here. Third frame, we're still seeing the ball. And then the fourth frame, we're going to predict where the ball might be in the next frame, right? So when I click on this and move to the next image, the ball should be where my mouse is. In this case, that didn't happen because the video skipped. And that's kind of an important point because it just tells you the assumptions you make have to kind of encode some information you have about the task, right? In this case, there's no way we could do anything about this. But because the arm moved from here to here instantly, and this happens, sometimes your sensors break or your camera might get stuck or like skip a few frames. Because the arm moved this much very quickly, now this algorithm is predicting that in the next frame, the ball is going to end up here, right? And that's not the case because the ball is not actually moving. She's still holding it. And so it kind of adjusts based on the fact that it didn't move, and it's now predicting it's going to be here. And right now, because our hand is covering the ball, we can't see the ball. But based on all this information, we're predicting that the ball is at this red location, and it will be in the future in this yellow location. And it's pretty accurate, right? We still can't see the ball. We're basing that it's here. The fact that she hasn't moved her arm, but she moved it previously, kind of tricks the algorithm. It thinks it's going up a little further, but it's not. So we have some bad predictions, but as soon as we see the ball, everything fixes itself again, right? So now she's going down, and since she has like non-jerky motion, like smooth motion, our predictions are good. So this is, I think, the best part. She's about to throw the ball, and you can see how the yellow is already predicting correctly where the ball might be, right? So it thinks in the next frame, the ball is going to be here, and she's not holding the ball anymore. So our prediction should be pretty good. And the ball is very close. It thinks it's going to be here in the next frame, almost there, then here, perfectly there, then here, and then here, and then here. If you can kind of see, it's kind of predicting what gravity does and how a projectile goes, because the higher up it went as the ball's slowing down, it's actually, and we didn't do any fancy math for this. It's just purely just looking at the average of the last 2 frames, right? And so far, so good. But as soon as someone holds the ball, we kind of mess everything up because there's a sudden stop, right? So it kind of tells you that you kind of need additional math to kind of average out all these noises. You might have some additional sensing to say, you know what, if I detect something in the way, then I know my predictions are going to go wrong. So there's so many other things you can add. But yeah, just play around with it. You guys have the code, you guys have the video. See if you can use the same technique to detect the blue ball and the green ball, right? You just have to change the color numbers for this, and maybe you can come up with a better equation for this as well. Right? And the final thing I want to show you guys, I think we have a couple of minutes left, is so your question might be, what do you do when I don't know what the color of the balls are? Like, what if I'm not trying to like I show this. Okay, so what I want to show you guys is this. Wow, this thing is all over the place. Yeah. Okay. So the question could be, what if I don't want to detect something that's just, one color? What if I want to detect a car, a person, Rubik's Cube, multiple colors, right? When you get into that problem, what you use is something called optical flow. The algorithms are there in OpenCV if you want to mess around with them. But these days, everyone is using deep learning, and this is kind of the state of the art right now with using deep learning. It's a lot faster. And what you actually do is the same thing we did with the ball tracking, just on a bigger scale. In the ball tracking, we only track the part where we detected the ball. But what if you track every single pixel in the image? That's what this is actually doing. It's looking at every single dot in the image and seeing how much they're changing. And what you get as an output is purely the change in the image, right? And what that helps you with is if there's motion in your images, you can detect it. Now, there's a different problem of like, how do I know what is the scissor, what's the hand? But at least you can detect all motion. And so if something is coming at you, if you have a self-driving car, you want to turn left, there's obstacles. This is how you get around that. It's called optical flow. And it's kind of cool. The images look really cool. So this is the new technique that they developed that's way better than what we used to have. So, yeah, so this is how they might do, car tracking or pedestrian tracking. Because once you track this section, you can then do the same thing we did before, cut out this section and then feed it into a neural network to then detect what is in there. Right? Anyway, so I guess that's my time. If you guys have any questions, let me know. I'm not sure who else is left. Probably no one here. Yeah. I'm not sure if you guys are here, Catherine and Rachel.
Yep, I'm here.
Starting to drive back to lab though. So.
Oh, okay.
Good
No
work.
worries. Yeah, I had no idea how many people were even there.
Yeah, thanks everyone who stayed to the end. I'll go ahead and end the webinar now, and have a great rest of your weekend, everyone. Bye.
Likewise.